It is not the best. All right. So first, everyone wave to Shelby, and then we can begin. So I still can't get the printer to work. Not that I tried that hard, but I'm gonna do my notes on my phone because we're just getting super techie in this class.
You got your phone out with your notepad with your phone laptop connected to the desktop.
Well, I just messaged myself my notes in a PDF. Super advanced.
21st century.
Yeah. Yeah. I do what I can.
You have an iPhone? 21st century. You still have
Yeah, it's an iPhone. Yes. You should think highly of me.
They're literally crapping on it the entire time. And it's hilarious. They're trying to love it, but they're just crapping on it.
All I know is that there are two things, well, I guess three things that people should never get in arguments about. Religion, politics, and Android versus Apple. Those are the three. Yeah.
What about family?
Okay, family as well. But never family and any of those. That's just out completely. You just can't do it.
And don't argue with the women, they are right, even if they are wrong.
I'm not going to touch that one. Okay.
Oh man. I just thought of our first couple lectures.
Mm-hmm.
Imagine what's the name? Intellectual positivism.
Oh, logical positivism?
Yes, logical positivism. Was that the one where if it isn't can't be proved by empirical data, it is not true?
Yeah, it's
Imagine my
nonsense.
wives.
Oh man, still not going to touch that. Okay. Oh man. Okay. So we're almost done with chapter 2. I'm actually working on chapter 3 already, and it's gonna be awesome. So, in case you didn't know this about me, I'm a system dynamics guy. So that's part of why this class makes sense for me to teach, is that it's uses system dynamics. Of course, like I said before, preferably you would have taken system dynamics before this class. However, we'll, instead of doing that, just teach it to you along the way. Sound good? Okay, great. It's actually really going to help your perspective on it. I think it's going to be quite good. I was worried about how it was going to shape up, and now I see a clear path forward. So that's going to be awesome. All right. So this is another of the lectures that comes from a Jupyter notebook. And we're going to use some of the same packages, load them in, but we're going to use them to do discrete Fourier transforms. So modern measurement systems primarily construct spectra, so frequency spectrum, like we've been constructing from Fourier series, the line spectra, and then with the Fourier transform with the continuous spectrum. So most modern measurement systems primarily construct spectra by sampling an analog electronic signal, y of t, to yield the sample sequence, yn, and perform a discrete Fourier transform. Because digital electronics are cheap now. Used to not be that way, but it is now. So very rarely will we do things analog anymore. We will sample it and then do it discrete. So the discrete Fourier transform, the acronym is DFT, of a sample sequence yn of length n is ym, where m's an integer, and this is how you compute each value of ym. Well, that's the definition. However, we won't compute it that way because, well, we won't compute it that way in an algorithm because it's way less efficient to compute it this way. In the 60s, somebody figured out how to compute it with a much better formula. So we don't use we don't use the definition to compute it anymore, but that's just an algorithm. This is the definition. The inverse discrete Fourier transform, or IDFT, reconstructs the original sequence for n being an integer and essentially summing up. And notice how similar this looks to the Fourier transform, right? I mean, it's very analogous with, instead of integrals, we have sums. Okay. Now, the DFT has a frequency interval equal to the sampling frequency divided by n. So WS divided by n, and the inverse discrete Fourier transform yn has time interval equal to the sampling time t. The first roughly half of the discrete Fourier transform values correspond to the frequencies. Scrolls in his notes, not texting or anything. Zero, the sampling frequency divided by n, 2 times the sampling frequency divided by n, all the way up to the sampling frequency divided by 2. And the remaining roughly half correspond to the frequencies. Negative sampling frequency over 2, negative n minus 1 times sampling frequency over n, comma, so keep going all the way down to negative sampling frequency divided by n. So it's kind of weird. Like the array comes out with like half of it being something that kind of makes sense with the frequencies, and the other half being negative frequencies. Like, but it's at the far right end, which is kind of odd. But it's how the formula gives us the components. In practice, the definitions of the discrete Fourier transform and inverse discrete Fourier transform are not the most efficient methods of computation. A clever algorithm called the Fft Fourier transform, or FFT, computes the DFT much more efficiently. Although it is a good exercise to roll our own FFT algorithm, in this lecture we will use SciPy's built-in FFT algorithm loaded with the following command. So we can just load it in. Pretty convenient. Now, given a time series array representing yi, the DFT can be computed literally by just saying FFT of y. So just like plug and chug, right? It's pretty nice. The only thing that you really gotta worry about is like what, you get this array out with the weird shifting stuff. So you have to sort of sort that out. There are a few other gotchas, and that's part of why the definition of this is pretty simple. But I wanted to walk through like an actual example where we dealt with these little gotchas that come up along the way in dealing with an actual FFT algorithm, FFT function. So in the following example, we will apply this method of computing the DFT. So, good. All right. So we'd like to compute the DFT of a sample sequence, yn, generated by sampling a spaced out sawtooth, okay? What I mean by that is we have a function that starts out looking like a sawtooth, drops down, and then instead of going right back up, it's going to have some blank space, and then it's going to have the sawtooth. So it's like a saw with like every other tooth missing or whatever. Okay? Let's first generate the sample sequence and plot it. So that's the first task, and we're going to do it in sort of a specific way that's going to allow us to do to avoid something at one of the gotchas. So we'll see it come up. We define the sampling rate, Fs, which defines the sampling interval, Ts. Furthermore, we define the frequency of the spaced sawtooth signal, F signal. So here's our sampling rate. So 200, we're using F instead of omega, so this would be 200 hertz, right? 200 hertz. That means that our sampling interval is going to be whatever 1 divided by 200 is in seconds. And the signal frequency is 10 hertz. So fortunately, are we expecting aliasing to happen here? Nah, we're good, right? We don't have to worry about aliasing because we're sampling at well over twice the frequency of the signal. Now, do we need to worry about it? So, are there potentially frequency components in this signal that are higher than our sample rate? Are there potentially any frequency components in this signal that are higher than the sample rate, or that the sample rate's not twice as fast as? So for instance, this signal is at 10 hertz, but that's just the fundamental frequency, right? There are the harmonics, higher harmonics, right? Every 10 hertz, there's going to be a component. It might be 0, but potentially there's a component. We didn't compute the Fourier series, so.
So what we're asking is that there could potentially be a greater or a higher frequency within this set.
That's right. Yeah, and I actually, so once you get out to the 10th harmonic, that's the last frequency for which our Nyquist sampling theorem allows us to say we don't have any aliasing for, right? So a sample rate of 200, that's only going to get us up to 10 harmonics without possibly getting some aliasing. But remember, aliasing is only going to be an issue if those are very big components, right? I mean, if they're really small. So like if you go up to like 10 harmonics and it's like 1/10 of 1/2 of 1% that's left up there at those harmonics, which a lot of times they do fall off. Not a big deal. We don't mind aliasing, like a little bit of aliasing that comes in. I mean, it's not ideal. We'd like to filter these things, but it's okay. So this is probably okay, but we're borderline. If we were sampling at 20 hertz, I would be pretty worried. We're sampling at 200 hertz, so like we're probably okay. Okay. We want an interval of ramp followed by an interval of space. So we're going to construct this spaced out sawtooth. The following method of generating the sampled signal y helps us avoid leakage, which we'll describe after the example. So we're going to do another little discussion after the example. We'll talk about leakage. But we're going to avoid that, and then I'll explain how we avoided it. So what we're doing here is we're saying we want an array of zeros, so we use this zeros method to create a half of a signal period worth of zeros. So an array with half of a signal period worth of zeros, and then we'll create another array with half a signal period worth of ramp function. And then we're just going to like concatenate them, right? We'll put zeros, and then we're going to put a sawtooth, and then we'll put a ramp, and we're going to put zeros, and we'll put a ramp. It's back and forth, right? So we'll initialize the time sequence y and initialize our j value here, which we're going to use as a sort of second index. So our main index is I. So for each sample, we're going to do this operation. So if the index, and then this is notation for if the index mod this value is equal to 0. What is so percent in Python is the mod function. What is the mod function?
The remainder?
It's very, very related to the remainder. It's essentially the remainder. Yeah, you could think of it as a remainder. So if you did mod of 4 and 2, using a different notation here, it's what it is you take the first number, you divide it by the second number, and whatever the remainder is, you are going to return for mod. So 4 divided by 2, it divides evenly in, right? So there's no remainder. So this would return 0. Mod of 5 divided by 2, mod of 5 comma 2, would return 2 goes into 5 2.5 times, right?
Yeah.
So it would return half of 2, which is 1, right? So it would return 1. Remainder 1. And that's what this is saying. So this is I mod. So instead of writing mod, they would write 5% 2.
So this is just giving us the value of the remainder.
Value of the remainder. So the remainder here is going to signal if we are at the start of a signal period. That's what Fs, the sampling frequency divided by the signal divided by 2, is what we're modding by. And we're saying, okay, are we at the start of a signal period with this index? And when it is, we go into this case. Otherwise, we just pass on through. We don't do anything. If j mod 2 is equal to 0, which happens every other signal period, right? Because what j we're going to, on the next sheet, we're just going to add 1 to j every time we come through here. So every other time, it's going to be the mod of j divided by 2 is going to be 0, because every even number can be divided by 2, right? And have 0 remainder. So it's true every other signal period. So we'll then append the zeros, and on the other situation, when it's not divisible by 2, so it's an odd j, so odd period, then we will use this else to say append the ramp. So half of it append the zeros, the other half append the ramp, and then back and forth. So you're just appending a bunch of zeros and ramps.
And that's how we get the thing on the top.
Yeah, and that's how we generate this graph right here. I mean, this is that plotted.
Yep.
So let's see that just quickly here. So the code comes up here. Okay, good. So from this sequence, we can compute the following parameters. So the number of samples is just computed by the length of y. The time array is just generated by saying, okay, it goes from 0 to ts, is just the total time. Oh no, so 0 to n times ts. Ts is the sample time. So n of those samples gives us ts times n, total range. What this says is create an array from 0 to n times ts with spacing of ts.
Can we do this function with any number that, like, so the first example was like 5 mod 2, but can you do like any series of numbers in the second value, so some, you know, some x value mod 23
Yeah. So then, like every 23rd,
harmonic?
every 23rd period, you could have a sawtooth show up. So it's kind of flexible. So you could generate spacing differently if you wanted to.
I'm just trying to make sure I'm understanding this in my head before I try to write anything down. It's just like,
Right.
you can use different values to space out or shorten your sawtooth, so to speak.
Yeah. Yeah. We are using this method. There are like 1,000 different ways we could generate this. This one is just one. Is one way. But yeah, I mean, it's a nice way. It's a nice way that's flexible. It allows us to say, okay, skip, every other period, but you could skip every other, or every other. So you could start spacing this thing out more and more if you wanted
This
to.
would be handy for, in the case of like a circuit, you could send a pulse to whatever spacing that you wanted, so you can go, at basically full bore for a certain amount of time, and then just go to 0 as soon as it ends that time, and then
Right.
they can space it out however you want.
Right. Yeah. So you could use this little snippet to generate if you changed like this 2 to a 3, like you said, or if you changed it to a 1, you wouldn't have any spacing.
Correct.
If you had spaced it to a 3,
Every third.
yeah, I think you have to flip the zeros on the ramp, but then every third one you would get a ramp, and then every fourth one, fifth one.
Alright.
Yeah, so it's a pretty nice way to do it, just for that reason. Okay. So good, and now we're going to plot this with the matplotlib that we've been using. So this is just open up a figure, plot the time array versus the time series, and blue, make it blue, and then a solid line with 2, x label is time in seconds, y label is yn, and that's what comes out. Pretty nice. Looks like we expected it to. Okay. Now, what we want to do is we want to generate this, right, the spectrum. So that's the next task. So display the plot with the following command. Show. Okay, now we have a nice time sequence on which we can perform our DFT. It's easy enough to compute the FFT. So we're going to use the Fft algorithm, which computes the same thing as it's the DFT, but just less computation.
Okay, question.
Yeah.
What is the FFT?
Ah.
Like in terms of formula?
So it looks a little different than this. It's actually not. It can't be easily expressed in a formula like this because it's an algorithm for computing these values. I don't think our textbook has it in there. It does mention it. I mean, it's something that you can look up. It's interesting to see it. It's very clever. It's like somebody was like, well, you like keep recomputing stuff in the main formula, so can we come up with a way of not recomputing things? And the answer is yes. And it's pretty much a fun thing to look at the algorithm, but it's not really that interesting to look at. Like that formula is pretty easy to understand. Like, oh, you just sum up a bunch of terms. The FFT is not as intuitive, but super effective. It's like, I forget the order. It's like log order, which is really good, of complexity, instead of like n squared, I think it is, for number of samples. Like the complexity goes up with the number of samples. I think for the regular DFT, I think it's order like number of samples squared. But I think that for the FFT, it goes up with like log of the number of samples. So it's a lot better, significantly better. Okay, so yeah, I mean, we could have come up with our own there. I would actually, encourage you, if you are interested, to you write your own little FFT algorithm. I mean, the algorithm is available wherever. It's not that hard to implement, really. I think you could write it, and then you could write your own function and do this with it. I mean, it's nice that their routines are already there for us, and we can just use them. But okay, so recall that the latter values correspond to negative frequencies. Okay, in order to plot it, we want to rearrange our Y array such that the elements corresponding to negative frequencies are first. It's a bit annoying, but c'est la vie. Like, this is just what we got to do. That's life, right? So Y positive and 0 is the values of Y. So we computed it, we got capital Y. So we're going to take essentially the first half, roughly the first half of them, call that positive and 0. And then for the negative, we're just going to take the positive one and delete the 0 out of it, which is something we had to do because the 0 is not in the negative ones. So it's a little annoying to have to do that. But that's all this does, is just delete the 0 out. Y positive 0 equals, it has a 0 and then other values after it. We want the other values, but we don't want this first 0. So that's why we do this part. We're just getting rid of that first 0. We're just saying, get that out of there. And then we're going to flip it, which is like that. Flip it. And then so that the order of these is all reversed. That's what this function is doing. This method's doing. And that is the whole thing, just lots of spacing. And then all we do is append the positive and 0 one to the negative, and we end up with one nice continuous spectrum, which is ready to be plotted versus frequency. That's the whole reason we did that, is so that they're in the right order to go into a spectrum. If we plotted it like this, it would look really weird, and it would be hard to interpret it. Okay, so now all we need is to find the corresponding frequency array, which is just an array that starts out at negative n over 2 plus 1, and it goes up to n over 2, scaled by fs over n. Okay, so that is remember back here when I wrote the frequency things? I'm essentially using these to generate, using these descriptions to generate these arrays, and now we just need to plot it. So the frequency total, which is what we just computed, absolute value of Y total, red and dash, line width is 2, X label is that it's frequency, Y label is that it's the spectrum, and now display the plot of the spectrum shown in the bottom of this figure. So this is what we got. So this is showing a bunch of zeros, and then there's, every once in a while, there's a non-zero component, and then there's zeros, and then there's a non-zero component. Zeros. And notice they build up to here, and it roughly looks like this, right? And if we had a higher sampling rate, we would have a better spectral resolution as well, and a wider bandwidth. So our points right here, these are all of the ym values, right? Now, it makes sense that at 0, so we got to interpret at least the first few of these. So if we look at the 0 frequency component, it shows up right here, right? 2 point something, 2.2 maybe, 2.1. That corresponds to the offset, right? It's the average value of this function if you take the integral over a period. So that's like somewhere like right here, which is roughly the average value of this function. This is the this is the fundamental frequency component. This should show up at whatever frequency this waveform occurs at, right? So that occurs at, it was 10 hertz, right? That's our sampling rate. There are 10 of these. 1, 2, 3, 4, 5, 10. 10 of these pulses in 1 second, so 10 hertz. So not surprisingly then, at 10 hertz, we have our first peak, our fundamental. And then we've got another one at a multiple of that, at 2 times the fundamental, 20 hertz, 30 hertz, 40 hertz. So at every 10 hertz, from then on up, we have a component. It's nice. I mean, it's conveniently correct. So that's good. We've got ourselves a nice spectrum. And that's really all from that. But I do want to have a note on leakage, which is the worst term for anything. It's just not a good term. Leakage. It sounds like one of those horrible, horrible drug side effects. Like, what? That's possible? Yeah.
Possible side effects include.
Yeah, no, like there's a worse term than leakage that is an actual side effect, but it essentially means the same thing. And I've heard it before in a commercial, and I was like, who buys this? Like, I don't know, maybe if it saves your life, but like still, it's kind of 50-50. Like, I'm not sure.
Are you gonna tell us what the term is?
Yeah, like you
Was it seepage?
Seepage! It's seepage!
I was like, it's only one thing that can be worse than that.
It's seepage. Why?
so glad you like called that out.
Potato chips.
Yeah.
What?
What?
If anyone gets that reference.
Wait,
At the very end of the movie, The Sweetest Thing, the guy sitting there eating potato chips. And the guy's like, oh, you know what those called? Or it causes leakage, right? It says right there on the bag. No one's ever seen this movie.
I've not seen this movie. Sorry.
About making potato chips out of
Pringles
leeks.
actually had to put that on their can.
Or leek flavored
Yeah,
potato
you're using a
chips.
type of fat that doesn't, your body can't break it down.
That's what it was in reference to.
Oh, yeah, well, since that fat.
Is that the hydrogenated?
It's 0 calorie, so it would just go right through you. Since it's fat, you can't really block it in. It's a lubricant, so it just.
Stop.
They had to put it on Pringles. Come on,
Ah.
stop.
I remember, I forget which comedian it was, but they said that about like Hot Pockets Express or something like that, and the directions are like remove from package, place in toilet. I thought that was funny. Okay.
How did we get to this round?
I don't know. It just descended from this word leakage. I couldn't even come up with a better title for this section. Just leakage. Okay. So the DFT assumes the sequence is periodic with period n, meaning that the entire series of data points that we have, the function is going to repeat that every time thereafter. An implication of this is that if any periodic components have a period less than n, unless n is divisible by this n short, spurious components will appear in the spectrum. So the way that I like to think of this is, imagine that you had a sine wave that you were sampling, and if you get up to one period, not one period of the sine wave, but if you got up to the end of your record and you had taken n data points, so dot, 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 all the way along, but you had a sine wave in here. I'm going to change color so it looks a little bit easier to see. That had a period of half that, or not quite. Say like little bit other than half. So like say it goes like up and.
You're never gonna get it perfect.
I know. Say it does this.
It almost comes down.
But it doesn't match up,
Sure.
okay? So it doesn't complete.
You did a good job.
Wait, do you want it to match up?
I don't want it to match
Oh,
up.
so it's supposed to be like progressively getting a smaller.
Oh no, that's not supposed to be that
But
way.
you think that like if
God damn it.
doesn't necessarily get to
But the period to those.
So what I want to have it do is this point right here doesn't match this point right here. So the algorithm assumes that you can just take this and copy it and stick it right there on the end. But if they don't match up, then it's assuming that you've got this action, which is not what you really have, right? Really, this sine wave continues, but the algorithm's assuming that these are going to match up. So if it doesn't match up, then you're going to have this so-called leakage, these terms that are going.
It's basically like a jump.
It's a jump, which actually that's going to bring in a bunch of high frequency stuff into your signal.
Is that what we would have? That's what you mentioned a couple of classes ago. Is like that noise you're trying to get rid of, right?
Well, it's a little different than noise in the sense that this is just this is a computing error. This is essentially like the algorithm's assuming that you're not doing this. And if you do this, if you give it the algorithm something that has this in it, then you screwed up. And you're going to have this happen. But, so it's sometimes difficult, though, when it's more than just a sine wave or a nice sawtooth, and you're just sampling something, to avoid this sort of thing from happening. To avoid leakage, it's difficult sometimes. So, instead of doing, so what we did in this last example is we constructed it so that they perfectly matched up, right? It's a sawtooth, which is fine. We did that on purpose. But when you're sampling something and it's just a measurement, you aren't always going to be able to say, oh, okay, I'm gonna stop my sample right there, and then I'm going to run the algorithm on it because it has the perfect match. That's not very practical. So instead, typically we use a window function to mitigate its effects. Effectively, windowing functions, or window functions, such as the Bartlett, Hanning, and Hamming windows, multiply our series by a function that tapers to 0 near the edges of the sequence. So here is a figure showing 3 different window functions and how they would be applied to our specific set data. And you see how this is, it's mostly 1 towards the middle, and then it tapers off to 0 or close to 0 on the ends. What it's doing is it's saying, I trust you here in the middle, not so much out here on the ends. And if you take, for instance, the Hanning, the red one, or the Bartlett, the blue one, you're going to perfectly match up on the endpoints by default because you're going to be multiplying these points, the other data points, by 0. So you're taking each of these data points and you're multiplying it by the other function. So if you can imagine superimposing our nice ramp function on here, we would be having like this ramp go up. I don't remember what the amplitude was, but let's say it was 1. It would be going up like there, and then it would be dropping down. No, I went too far, didn't I? Try that again. Going up to there, and then it would be dropping down. And it would be going over. And then it would be going up. Right? This is the function that we have that we're going to apply this window function to. So we're going to multiply this value, whatever this peak is, by whatever the corresponding value is here. So these, in other words, this window is going to shrink these guys down to like there, right? So the ones at the ends are going to get really damped out. The ones in the middle are going to come through. And that helps improve this leakage, but it's not ideal. We don't really want to mess with our function. But it's in practice the way that we deal with it. Another way to mitigate things is to just have more data. That helps too. So the more data we have, the better. Higher sampling rate, larger N, but that's the idea. So there are several that are available in NumPy windowing functions, so you don't even have to, do anything besides just call up the library. And so for usage information, I thought I would show you guys this idiom. Just put a question mark afterwards and evaluate it, and it'll give you like, here's how you do it, and here's an example. It's kind of nice. Sort of like in MATLAB, the help function. Help, whatever. The question mark at the end does that. So then this is just me plotting this. So these are just the Bartlett window, the Hanning window, and the Hamming window. I just evaluate them, and you just give it the number of data points you have. It returns it. I should have plotted the original Sawtooth windowed, though. That would have been sweet. Like this shrinking thing. Ooh, that would be fun. I should do that.
Post it in Slack.
Post it in Slack. I feel like if somebody goes through and generates one of these and windows this function and post it to Slack, I will give you bonus points in the class. Legit bonus points. Realsies ones. You can count towards your grade. No! There will be multiple points. It will be the first person to post one that's working on Slack. I will give 3 bonus points on the first midterm exam.
How many points is a midterm?
100.
Oh.
3%. And for everybody who posts one thereafter, so that it's not like a lost cause if you see somebody else put one up, I'll give a bonus point to everyone who puts a successful one up. But the first one gets 3. Ooh.
We're trying to build that thing.
Kind of.
Trying to build this one. So take the function that we created. You can reuse all of this code if you want. And then you just need to window it with the Hanning or Hamming or Bartlett or any of these window functions, and then plot it.
So that
Yeah.
distributes it evenly over, like you did it at 1 second with our sampling rate, but
Right.
it would do it over whatever time interval you wanted to
Totally.
sample something.
So if you sampled for like 100 seconds,
The median would be 50, and it would peak
Yeah.
at 1 at 50, and it would give you the exact value that your function ran out at 50
Totally.
seconds. But everywhere else, it would multiply it by a factor that they're saying we don't really like you less and less.
right. We trust you less and less. We feel like you might cause leakage.
So how does this solve something like where your sine wave ended kind of funny? What
Yeah.
would it look like adjusted?
So if we were to do that, and you could imagine that for instance, this is the offending stuff right here, right?
Right.
So this would be tapered down to 0, and instead of coming out here, I'll use like orange.
So the wave function would just grow closer to 0 at each,
Yeah, it would go more like this.
and as you backtracked, it would grow towards the middle, and then
Yeah,
shrink back.
and then it would be shrink back down to this. But it sort of makes it so that no matter where you are at the endpoints, it's going to force you to go to 0
Okay.
so that it repeats.
So is that like an oscillating exponential kind of thing? Where, I mean, it wouldn't grow infinitely in the middle, but it grows slowly bigger towards the middle and then it decays towards the end?
I don't remember the functional form of the Hanning and Hamming, and there are a few others. It could be like an e to the minus x squared kind of thing, which is a normal distribution. It looks a little bit like a normal distribution. It might be. I don't know for sure. I don't remember. If I had paid more attention when I typed this in, I probably would know. Yeah.
But you were
Cool.
a whole day early doing the notes.
I know. I'm working today on Wednesday's notes.
My
Can you believe that?
Dude,
You're gonna get distracted.
This
you got
is,
tired of having to paper printing.
yeah. Clearly, I am, I don't have enough to do because I'm like a full 2 days ahead. Or actually, what I like to refer to as on time. Not used to it, though. This is unfamiliar
You're
territory.
still 2 minutes late to get into class.
I mean, I can't be perfect. I don't want to like set up this too high of an expectation from you guys.
So your fancy sock tooth plugged in to